Every morning, millions of Americans unroll a sheet of toilet paper without ever stopping to wonder, where does this everyday product actually come from? Behind those 140 rolls the average person uses each year lies one of the most massive industrial supply chains on Earth. It all starts right here, in forests grown like crops. Welcome to the first chapter of the best-kept secret in our bathrooms, the birth of toilet paper. This is where it begins, not with an axe, but with cutting-edge machinery. The Feller Buncher. GPS-guided, laser-equipped, hydraulic arms that can fell, limb, and stack a tree in under 10 seconds. Watch the cutting head, grabs the trunk 5 meters up, saws clean through in a flash, then gently lays the tree down exactly where it needs to go. No waste. No chaos. These are certified FSC or SFI plantations, replanted at a 2-to-1 ratio or better. In the United States, about 70% of the wood used comes from managed forests. Roughly 70% hardwoods for softness, 30% softwoods for strength. Important nuance in modern mills. Up to 50% of the raw material now comes from recycled paper. Fewer trees cut, shorter fibers. It's a trade-off the industry keeps refining year after year. The logs head to the mill, sometimes by the trainload, at massive facilities like those run by Georgia Pacific or Kimberly-Clark. The industrial process takes over. First stop, debarking. This enormous drum spins at 6 and level shoots per minute. The logs tumble and rub against each other, stripping the bark almost completely. Result: 95% of the usable wood is preserved. The bark itself becomes biomass fuel to heat the mill's boilers. Circular economy from minute one. Once stripped, the logs move to the chipper, a monstrous machine with 10-foot diameter rotating knives. In seconds, an entire log is reduced to thousands of uniform 2-3 centimeter chips. These chips, up to 50 tons per hour on a big line, are conveyed toward the digester. That's where the real chemical magic begins. The digester, a pressurized chemical reactor the size of a small building. Chips are mixed with cooking liquor, caustic soda, and sodium sulfide, heated to 170 To C, 338 To F, under pressure for 3 to 4 hours. The lignin, the natural glue that holds wood fibers together, dissolves. What's left? A brownish, fibrous slurry, raw pulp. 50 tons of chips go in, roughly 25 tons of pulp come out. The rest, steam and heat recovered to power the mill, plus black liquor, burned to generate energy and recover chemicals. Maximum efficiency. But this step is heavy. It demands huge amounts of water, energy, and it generates CO2. Modern mills recycle 80–90% of the water and capture a portion of emissions. Edge case, recycled pulp lines skip this intense chemical digester altogether, but they produce shorter fibers that are less soft. We now have raw pulp, a fibrous brown soup, still very far from the bright white soft tissue you know. But the journey is just getting started. In the next episode, we dive into the chemical transformation, bleaching, and refining, turning this dark mush into pure, bright stock, ready to become a sheet. We left off with raw pulp, a brownish, fibrous slurry, still loaded with lignin, the natural glue that gives wood its dark color and binds the fibers together. But the toilet paper we use every day is bright white and soft. How do we get from this murky soup to a clean, pure base, ready for sheet formation? This is where the real chemical alchemy happens, in the heart of the modern mill. Welcome to Episode 2. Bleaching and Refining, where science meets massive-scale industry. First mission: cleaning and purifying. The raw pulp still carries leftover lignin, tiny metal particles, and other impurities. It passes through a series of screens, centrifugal cleaners, and pressure screens that spin out heavy contaminants. This initial cleanup prevents defects later in the process. But the dramatic color change? That comes next. Bleaching. In today's modern mills, bleaching happens in a series of 3 to 5 stages inside these towering reactors, each one 60 to 100 feet tall. Decades ago, elemental chlorine was common, but it produced toxic dioxins. The industry shifted hard. Most facilities now use ECF elemental chlorine-free, or TCF totally chlorine-free, processes. The main agents? Chlorine dioxide, hydrogen peroxide, ozone, oxygen under alkaline conditions, or combinations of them. Here's what's happening chemically. Oxidizing agents attack the chromophores, the molecules responsible for the brown color, and break them down. The pulp moves from dark brown to a brilliant white, often reaching 88–92% ISO brightness. In a large Kimberly-Clark or Georgia-Pacific facility, a single tower can process hundreds of tons per day. Important nuance for recycled pulp lines: bleaching is gentler and more limited because short fibers degrade faster under strong oxidants. That keeps costs higher but lowers environmental impact. Each stage uses significant water, roughly 40–50 gallons per pound of pulp, and energy. But modern plants recycle 85–95% of that water in closed-loop systems and scrub exhaust gases to capture emissions. Real-world implication: while far cleaner than the chlorine-heavy processes of the 1980s and 1990s when dioxin scandals hit headlines, bleaching remains energy-intensive and contributes to the paper industry's overall carbon footprint. Edge case: fully TCF bleaching, zero chlorine compounds, is greener and produces effluent that's easier to treat, but it can leave the pulp slightly less bright. Some eco-brands accept that trade-off willingly. Now the pulp is white, but the fibers are still too loose and unbonded to form a strong, uniform sheet. Enter refining, a mechanical beating process that prepares the fibers for papermaking. The double-disc refiner works like an industrial blender on steroids. The two discs, spaced just fractions of a millimeter apart, shear and fibrillate the fibers as they pass between the grooved surfaces. This creates tiny fibrils that improve fiber-to-fiber bonding, increases sheet strength, and enhances softness. At this stage, additives are often introduced: starch for dry strength, retention aids to keep fines in the sheet, defoamers to prevent bubbles. For premium toilet paper, refining is tuned aggressively to maximize bulk and absorbency. Nuance: over-refining makes the pulp too dense and brittle. Under-refining leaves a weak, fuzzy sheet. Operators fine-tune in real time using AI-monitored sensors that measure freeness, drainage, and fiber length. At the end of this episode, we have purified, bleached, and refined pulp stock. Bright, clean, and ready to become a thin, continuous sheet. But there's still 99.5% water that needs to come out. In Episode 3, we witnessed the near-magical birth of the paper sheet itself, from liquid slurry to a fast-moving web at over 3,000 feet per minute. We now have bright, refined pulp stock, clean, white, and full of prepared fibers. But it's still 99.5% water, basically a very thin soup. In the next few dozen feet of this machine, that soup will become a continuous sheet of paper, moving faster than a person can run. This is one of the most visually spectacular steps in the entire process. Welcome to Episode 3, The Birth of the Sheet, where liquid turns solid at over 3,000 feet per minute. Everything starts in this large mixing chest, the machine chest or stuff box. Here the refined pulp is diluted even further with whitewater recycled process water to about 0.30–0.6% solids. Pumps push this dilute stock toward the most critical component, the head box. The head box, or flow box, is the precision heart of the machine. Modern hydraulic headboxes distribute the stock evenly across the full 18-26-foot width of the wire. Adjustable slice lips control the jet speed and thickness, matching the wire speed to minimize turbulence. For multi-ply toilet tissue, some machines use layered headboxes, one for soft outer plies, another for stronger inner plies, laying them down simultaneously. The goal: uniform basis weight and perfect fiber orientation from the very first instant. This is the famous Fourdrinier wire, the forming fabric that has defined papermaking since the early 1800s. As the dilute stock hits the wire, gravity, table rolls, and high-vacuum suction boxes pull water through the mesh. Within just a few feet, solids content jumps from under 1% to 15–20%. The fibers mat together into a wet web that can finally support itself. Modern twin wire or gap formers sandwich the stock between two wires for even faster drainage and symmetrical sheet structure, especially useful for high-speed tissue machines. Next comes pressing, the most energy-intensive dewatering step. Multiple press nips apply enormous pressure, up to 1,000–2,000 pounds per linear inch. The wet web travels between thick felts that absorb and carry away water. By the end of the press section, moisture content drops to 45–55%. Advanced shoe presses and vacuum systems squeeze out even more water, while preserving bulk, critical for soft toilet tissue. Recovered press water is filtered and reused, often making up 70–80% of the dilution water back at the headbox. The final drying stage, the Yankee dryer. This massive mirror-polished cylinder is the signature of tissue and toilet paper production. The still wet web is pressed onto the hot surface around 250–300 fshe via pressure roll. Steam inside condenses, transferring heat to evaporate water in seconds. A large gas-fired or steam-heated hood above removes the vapor. As the web dries, it shrinks slightly and adheres more tightly. At the end of the cylinder, a doctor blade, the creeping blade, scrapes the sheet off, creating the characteristic crinkled texture that gives toilet paper its softness, bulk, and absorbency. Creeping ratio sheet length before vs. after creeping is tightly controlled, typically 20–40%, to balance strength and softness. By the end of this section, we have a continuous dry sheet, crept, soft, and ready for finishing. But it's still a giant, unperforated, unembossed web, many feet wide. In Episode 4, we enter the converting area, embossing, perforating, and rewinding, where this raw tissue becomes the familiar rolls we buy and use every day. We've reached the point where the giant, plain tissue web, dry, crept, and miles long, finally becomes something recognizable, the soft, perforated rolls we grab off the shelf. This is the converting stage, where raw paper meets artistic engineering. Welcome to Episode 4. Embossing, perforating, and rewinding, the steps that turn an industrial web into the everyday product we all know and use. Everything starts with unwinding the massive parent roll. Modern rewinders handle these 5–10-ton monsters at speeds up to 2,000–3,000 feet per minute. Automatic tension controls, dancing rollers, and laser-guided edge detectors maintain razor-sharp alignment. Any flutter or misalignment here would ripple through the entire downstream process. The web is now ready for its defining features. Embossing. This is what gives toilet paper its signature texture, bulk, and perceived softness. The engraved roll presses the web against its counterpart, creating permanent raised patterns. These aren't just decorative, they serve real purposes. Increasing sheet thickness, bulk without adding more fiber, trapping air pockets for better absorbency up to 20–30% improvement, and separating plies slightly so they don't stick together when wet. Premium brands use deep, multi-level quilting patterns. Economy rolls often have simpler microdots or pin embossing. Nuance. Embossing must be carefully balanced. Too deep, and the web weakens, or tears too light, and you lose the premium feel. Recycled fiber sheets are more delicate and usually receive gentler embossing to avoid fiber damage. Edge case point-to-point embossing aligns patterns on both sides of a 2-ply sheet for maximum bulk and softness, with minimal fiber use, a favorite technique for high-end brands. Implication: good embossing can reduce the amount of pulp needed by 10–15% while maintaining or improving consumer perception of quality. Right after, or sometimes integrated with embossing, comes perforation. A high-speed rotary blade with finely tuned teeth creates tear lines every 4–5 inches, the standard sheet length. The goal is effortless tearing with minimal force, yet the web must remain strong enough to wind and transport without breaking. Modern perforation systems use servo-controlled blades and vision cameras to ensure perfect alignment and depth. Nuance: perforation. Depth is critical. Too deep, and rolls can tear prematurely in packaging, or transit too shallow, and users struggle to tear a single sheet. Some advanced lines experiment with variable perforation spacing or wavy patterns for softer tear feel. Implication: well-designed perforations reduce paper waste at home. People are far less likely to yank off 3 sheets when one tears cleanly. Now, the rewinding itself. The web is wound onto a core, usually recycled cardboard, or formed coreless by tightly controlled folding and compression. Pneumatic systems and rider rolls control density. Too tight, and the roll feels hard and difficult to unwind. Too loose, and it collapses on the shelf. Modern rewinders switch cores and cut the web automatically in fractions of a second, producing finished logs at rates of 60–100 per minute on high-end lines. Nuance: coreless rolls save 15–20% on cardboard material and reduce landfill waste, but require tighter control to prevent crushing. Edge case: some lines add light lotion or fragrance applicators, here though rare for standard toilet paper. Implication: the entire rewinding process is now heavily automated and touch-free for hygiene, a direct legacy of pandemic-era demand for maximum cleanliness. At the end of this episode, we have long, finished logs, embossed, perforated, wound with precision. All that remains is to slice them into individual rolls, package them, and send them out into the world. In our final episode, we'll cover the last steps: cutting, packing, quality control, and zoom out to the bigger picture and environmental impacts, innovations, and what the future holds for this ubiquitous product.